Now let's discuss about the methods for determination of electronegativities. Some of the methods known for the determination of electronegativity are discussed below. Firstly, we use the Pauling scale of electronegativity. Linus Pauling, who was born in 1932, was the first to propose the scale of electronegativity on the basis of bond energy. According to Pauling, and purely covalent bond, that is 100% covalent, the bond energy of a molecule is energy of geometric mean of the bond energies of the atom A and B, where delta is the extra bond energy and it measures the polarity of the bond AB, which depends upon the electronegativity of atoms A and B. This excess bond energy arises due to the resonance between the covalent structures AB and the ionic structure A dash A positive and B negative, which is also known as resonance energy. By calculating the delta E for different bonds, Pauling scale suggested that the following empirical expression to correlate the delta E with the electronegativity of the atoms XA and XB, where delta is the excess bond energy which is measured in kilocalorie per mole. However, if delta E is expressed in electron volt, the above expression reduces to but experimental value of bond energy is greater than the calculated value. The difference in the value is given by the delta. In SI unit, the relation becomes rho electronegativity of A minus electronegativity of B is equal to 0.088 delta E under root. Assuming an arbitrary value of X to hydrogen as 2.1, the Pauling was successful in getting the suitable values for the elements from chlorine to fluorine in the range of 2.5 to 4. The Pauling scale of electronegativity are given in the table 2.12. Now let's discuss variation of electronegativity. Electronegativity varies slightly from compound to compound. For example, the electronegativity of carbon in methyl chloride is 2.4 and the electronegativity of chlorine in carbon tetrachloride is 2.6. Thus, the electronegativity is a variant property and shows significant dependence on its environments. Electronegativity depends on several factors discussed below. Oxidation state. The electronegativity values depends upon the oxidation state of the atom in the molecule. As the oxidation state of an atom increases, the attraction for the electron increases, so the electronegativity should also increase. Given in the table 2.12, below are the values of electronegativity with different oxidation state. Thus, the electronegativity increases as the positive oxidation state of an atom increases. This is in the agreement because with the increase in the oxidation state, the tendency of the attraction of electron increases. Pauling electronegativity values, for example, for a ferric second is 1.83 and ferric third is 1.96. Hybridization. The type of hybridization used in the molecule affect the electronegativity of an atom. This is because s orbitals, because of their penetrating power, are more nearer to the nucleus compared to p, d and f orbitals. As a result, s orbital will have the lower value and hence should have higher oxidation state. Thus, with increase in the S character in the different organic compounds, the electronegativity of the carbon increases. This can similarly be extended to nitrogen compounds. For example, the electronegativity of nitrogen in sp3, sp2 and sp configuration shows an increase in their values of 3.7, 4.1 and 5.1 respectively. It is increasing to note that then sp hybridized at nitrogen compound has more electronegativity than even fluorine. Periodic trends of electronegativity. A careful inspection of the table 2.11 reveals that on moving across a period from left to right in the periodic table, the electronegativity values increases. This is due to increase in the effective nuclear charge and decrease atomic size. Electronegativity's values are found to decrease as one moves from top to bottom in a group. This is because down the group the size of an atom increases and therefore the effective nuclear charge decreases. There is a clear trend in the electronegativity values in the periodic table. Non-metals that gain electron to complete their octet outer shell have greater electronegativity values than the metals which prefer to lose electron to achieve the full outer shells. Electronegativity values are generally decrease as the atomic number decreases down a group. They increase as the atomic number increases in a period. When an electronegativity values are plotted against the atomic number, it is inferred that the strongest non-metal, that is the halogen, appear at the peaks, whereas the alkali metal represent the troughs, which is shown in figure 2.10. Thus, all the alkali metals have low electronegativity, whereas the halogens have the highest electronegativities. In brief, the electronegativity's value generally increases on moving down a period and decreases on moving down a group. Chemical properties and the periodic table. Electronic configuration help us to understand changes in an atomic radii, ionization energy and electronegativity across the period from left to right and down the group top to bottom in the periodic table. On the other hand, the ionization energies and the electronegativity help to understand the chemical reactions. Let's see how our knowledge of electronic configuration along the ionization energies and electronegativity help in understanding the chemistry of the elements and their compounds. There are three ways in which the periodicity of and chemical properties can be discussed. The first compares the properties of the elements moving down a group. The second compares the properties moving across a period. The third compares the elements that are diagonal to each other. And now let's discuss how do the properties change down a period and across a period. Change in properties down a group. The chemical reactivity of the main group metals increases as the ionization energy decreases from top to bottom in a group. The decrease in the ionization energy is due to the increase in the size of the atom along the effective screening. Owing to the effective shielding, atoms at the bottom of the group lose one more their outer electrons easily than the electrons near the top. This happens even in group to the right of the periodic table, which we generally associate with non-metals. For example, in group 15, the non-metals nitrogen and phosphorus are near in the top, but by the time we reach bismuth at the bottom, distinct metal character is present. Thus, we generalize that metallic character increases down a group. The immediate consequence of metallic character is reflected in the ionic nature of compounds. Change in the properties across a period. Across a period, the number of protons in the nucleus increases with the corresponding increase in the number of electrons. This also happens down in a group, but with a difference. In case of a period, the number of electrons are being added in the same shell, whereas in the case of a group, the electrons are added in the new shells. As a result, the nucleus exerts a strong attractive forces on the outer electrons. This results in the atomic radii to decrease. Consequently, the effective nuclear charge, ionization energy, and electronegativity values increase, and the atoms lose electron with increasing difficulty. In exceptions for the noble gases, atoms prefer to gain electrons more readily. In chemical reactions, metal tends to lose electrons whereas non-metals tend to gain electrons. It means that atoms change from metals to metalloids to non-metals from left to right across every period of the periodic table. With this change, a change in chemical behavior of hydride, oxide and chloride of elements is reflected in a periodic manner. These changes in the metallic and non-metallic character are summarized in figure 2.11. It is easy how to appreciate how cesium and francium are the most metallic, whereas the fluorine and chlorine are most non-metal in the periodic table. This periodic and systematic change in the metallic to non-metallic character is reflected in several chemical properties, especially towards the reducing and oxidizing character. As already discussed, the metallic elements appear in the left-hand columns and non-metallic atoms appears at the right-hand columns of the periodic table. Metallic character has been shown to decrease from left to right in the periodic table. It is also seen that the metallic character of the elements in a family group that is not constant but increase with increasing atomic number. For example, in group 14, the carbon, silicon and germanium have mainly non-metallic character, whereas tin and lead have mainly metallic properties. Thus, the metallic properties of the elements vary in a systematic manner. This is further reflected in the acidic and basic character of the hydrogen compounds as shown below. Acidic and basic character of hydroxide. The acidic or basic character of the hydroxide depends upon the location of the elements in the periodic table. In general, is dioxide of the metals combined with water to form hydroxide that are basic, whereas that of non-metals combined with water to form the hydroxide that are acidic. Acidic and basic behavior of the hydroxide of the second and third periods of the elements are shown in the table 2.13. The oxides of an element become more acidic from left to right on across a period and more basic from top to bottom down a group. The trend is exactly similar to that of hydroxide. The change from the basic to acidic character can be explained on the basis of increasing electronegativity of the elements on one moving from left or to right across a period as shown in table 2.14. It is interesting to note that we do down the group the basic character of the oxide increases. This increase in the basic character of the oxide is due to the decrease in electronegativity of the concentrated concerned element. Table 2.15 shows the trend in the variation of acidic and basic character of the oxide in group 1 alkali metals and group 2 alkaline earth metals and the group 13 boron family atoms. Trend in bonding between elements in the periodic table. The nature of bond, covalent or ionic, influences the chemical behavior of the compounds. If two compounds forming a bond having similar electronegativity, that is similar tendency to attract electron, the bond formed will be predominantly covalent. On the other hand, the large difference in the electronegativity leads to a bond with high degree of polar character, that is the bond is predominantly ionic. Hydrogen halides. According to the polling, when the electronegativity difference between the two bonded atoms is 1.7, the bond formed is 50% ionic. If the difference in the electronegativity increases, the bond trends be more and more ionic. Since the electronegativity difference between the hydrogen and chlorine is 0.9, the ionic character of the bond between the hydrogen and chlorine is approximately 17%. Thus, as one processed in the group 17 halogen family, the electronegativity of the halogen atom decreases and consequently the electronegativity difference between the hydrogen and halogen in the HX axis chlorine, fluorine or bromine iodine decreases. As a result, the ionic character decreases accordingly. Halides of main group elements. Main group elements are well known to react with halogens to form metallic halides. The properties of these halides also display a gradual change from ionic to covalent character because of electronegativity values. The halides of alkali metals are ionic nature. As one proceeds along a period, the covalent character of the halides start increasing. For example, in the second period, lithium chloride is a typical ionic solid, whereas the carbon tetrachloride is typically covalent. As move one down a group, the degree of ionic character in the halides increases. This is primarily because of the increase of electronegativity difference shown in the table 2.13 is the graphical sketch of display trends in bonding between the main group elements and the halogens. It is important to note that the chlorides, the oxides, as well as hydride show similar trends. In brief, the oxides, chloride, and hydrides all become more covalent from left to right across a period and more ionic from top to bottom. Trend in oxidizing and reducing character. Oxidation is a process in which electrons are lost, whereas the reduction is a process in which electrons are gained. Thus, when a substance gets oxidized and electrons are lost, when the substance gets reduced, the electrons are gained. It means that oxidizing agent is a substance which gains electrons, whereas a reducing agent is a substance which loses electron. Thus, the tendency to lose electron depends upon the ionization energy. It is easier to remove the electron from a larger atom than a smaller one. Alkali metals, being larger in size, have strong tendency to lose electron and are therefore strong reducing agents. On the other hand, halogens atoms present on the right side of the periodic table having a strong tendency to accept electrons and therefore are strong oxidizing agents. We have learned that information from the table 1 figure 1 2.13 while discussing the metallic and non-metallic behavior change in the periodic table. Thus, moving down a group, reducing character increases and oxidation character decreases, and moving across a period, oxidizing character increases and reducing character decreases. However, while explaining oxidation reduction in next solution, we talk of the oxidation reduction potentials. The strength of the oxidizing and reducing agents are measured in the terms of the size of the potential between a solution to a inert electrode. The standard electrode potentials of the same of the S and P block atoms are shown in the table 2.17. The standard reduction potential measures the tendency for the reduction occurs as the standard reduction potential are written by the IUPAC convention with the oxidization species on the left and the reduced species on the right. If the value of the standard electron potential is less, the substance will not be easily reduced. Instead, it will be oxidized and thus form a strong reducing agent. For example, in case of sodium, the reducing potential has a value of minus 2.71 volt, whereas in the case of lithium, the reduction potential has a value of minus 3.04 volt. The lithium is a better reducing agent than the sodium. Similarly, the reduction potential of bromine is 1.36 positive and that of fluorine is plus 2.85. It means that fluorine is better oxidization reagent than bromine. A close inspection in the table reveals that alkali and alkali earth metals have large negative reduction potential as compared to that of groups. Therefore, elements of group 1 and 2 are strong reducing agent, and on the other hand, halogens have the strong large positive reduction potential. They are strong oxidizing agents. Across the period, there is a regular trend in the reduction potential, that is, value of E naught becomes less negative. Therefore, the reducing character decreases and the oxidation character increases. Thus, lithium is a stronger reducing reagent while the fluorine is the stronger oxidizing agent in the second period. Oxidation states. Oxidation state of an element in a compound is related to the number of the valence electrons present in the outermost shell. During the formation of a bond in a chemical reaction, electrons may be donated or accepted by atom depending upon the relative ionization energy and the electron affinities of the combining atoms. The combined atoms and ions of the main group elements often have the same electronic configuration as that of the noble gases. In order to predict some common oxidizing states for atoms, the main group elements, one should determine the number of electrons that could be donated or accepted by the atom in achieving the noble gas configuration. For example, atoms belonging to group 1 and 2 acquires the noble gas configurations by losing 1 and 2 electrons respectively. Therefore, these elements acquire the oxidation states which are always same as the group number. Thus, we label the alkali metals with oxidation state plus 1 and alkaline earth metals with oxidation state plus 2. Similarly, the plus 3 oxidation state is exhibited by the elements of group 13. On the other hand, elements belonging to group 15, 16 and 17 have a strong tendency to gain 3, 2 and 1 electron respectively to acquire NS2 and NP6 configuration. Thus, the element of these groups exhibit -3, -2 and -1 oxidation state respectively. In case of p block elements, the oxidation state is normally either the group number 10 or 18th group number. To assign the oxidation state in a polar covalent bond, it is assumed that the shared pair electrons is owned by the more electronegative atom. Then we compare how many outer valence electrons of an atom possesses in a molecule or ion with the number of electrons it has in the free monatomic element. The difference between the number of the valence electron possessed by the free atom minus the number of the valence electron is the oxidation state. For example, the oxidation state of oxide ion is -2. Variation of the oxidation state across a period. There is a regular trend in the oxidation state of the main group elements. This is perhaps one of the most systematic periodic trend as shown in the figure 2.14. Across a period from left to right of the periodic table, the positive oxidation state increases stepwise and the negative oxidation state decreases. The maximum positive oxidation state is the number of electrons in its outermost shell. For example, in the second period, the oxidation state increases from lithium to carbon from 1 plus 1 to plus 4, and then decreases from nitrogen to fluorine, that is from minus 3 to minus 1. Similar trend can also be seen in the period 3 when the oxidation state increases from sodium to chlorine plus 1 to plus 7, and then decreases to silicon to chlorine, that is minus 4 to minus 1. Variation in a group. There is no variation in the oxidation state of group 1 and group 2 elements down the group. In fact, all members of the alkali metals have plus 1 oxidation state, where all members of alkaline earth metals exhibit an oxidation state of plus 2. P block elements show normally oxidation state equal to the group number 10 to 18. In addition to the usual oxidation states, some of the P block elements, especially the higher members, also show another oxidation state which differs from the oxidation state by 2 units. P block elements show normally the oxidation state equal to the group number 10 or group number 18. In addition to the usual oxidation state, some of the P block elements, especially the higher members, also show the another oxidation state which differs by the normal oxidation state by 2 units. Let's take the group with 13 elements which have 3 valence electrons. 2 of the valence electrons are in the p subshell, whereas the third one in the p subshell. Therefore, the normal oxidation state of this group is plus 3. However, the heavier members of this group, especially indium and thallium, show the another oxidation state is plus 1. The cause of stability of lower oxidation state down the group can be explained on the basis of inert pair effect. In case of thallium, after the removal of one electron from the p orbital, the remaining 6s2 pair of electrons do not participate in the further in bonding, unlike the other lighter members is like boron, aluminum, etc. In other words, electron in the 6s2 behave as inert and is responsible for the name inert pair effect. Similarly, the electron pair 5s2 in case of indium does not participate in bonding and is called inert pair. This effect is restricted to group 13 alone, but also occurs in heavier elements of group 14. As a result, tin and lead exhibit an oxidation state of plus 2 in addition to the normal plus 4 oxidation state. It is important to note that the lower oxidation states are more stable than that of higher oxidation states. Thank you. I have completed my chapter, The Periodic Properties.